Welcome to Architectural Insights with KING-KAMBUF. This is your daily interdisciplinary mentorship brief for Wednesday, December 3rd, 2025.
Hello.
This is designed for you,
Mm-hmm.
for the architect, the engineer, the planner, the leader, who really needs to operate at that, that high-level command space.
Mm-hmm.
We're taking this huge, complex stack of global intelligence, and we're just pulling out the insights that sharpen your command. We're talking structural physics, policy, everything in between.
Exactly. And our mission today is really to synthesize all this material and to focus on the radical interconnectedness of what seem like completely disparate forces.
Right.
We're going to be treating climate, politics, material science, even airflow as if they are structural problems.
I like that framing.
Yeah, we have to jump straight in and recognize how a microbiofilm on a facade in Yakutsk connects intellectually to a massive governance challenge in the Pacific Rim. It's a breadth that, it demands a really high-level focus.
Okay, let's unpack this. We're starting with a scan of the globe, the latest industry pulse. And we're zeroing in on three areas where AEC leaders are really pushing the boundaries.
Right.
First up, cold climate innovation. We're moving beyond just, resisting the cold, and we're actually getting into using it. Specifically, turning snow into an active, luminous architectural asset.
So the first innovation we're tracking is this really sophisticated daylighting strategy they're calling solar rebound skins.
Solar rebound skins.
Yeah, and it's being actively tested in high-latitude cities. Think Helsinki, Murmansk, Calgary, places where sunlight is scarce, but the ground reflectivity, thanks to all that snow, is abundant.
What's so fascinating here is how the system really gets at that persistent problem of low-angle winter sun.
Mm-hmm.
So instead of designing a facade to just capture direct overhead light, which, barely exists in the winter in those places, these specialized facade laminates are actually engineered to harness the reflected light.
The light bouncing off the snowbanks?
Exactly.
Yeah.
Bouncing off snow, off ice, and then redirecting it deep into the interior. We're talking about utilizing up to, 80% of the ambient winter light that before just hit the underside of the first floor.
The efficiency gains are just tremendous. It translates directly into a reduced electrical lighting load right during those peak winter hours. But the engineering challenge is far from simple.
Okay.
We have to address the facade-spandrel interface.
And why does that specific intersection matter so much?
Well, when you maximize the capture of this really intense low-angle reflected light, you are directing a powerful concentration of thermal energy right where the glass meets the opaque perimeter elements.
The upper mullions.
Specifically the upper mullions, those vertical members holding the glass. If we get the geometry wrong, the material bounces too much shortwave radiation onto them.
And that causes what? Intense, localized heat?
Intense, localized, and potentially inconsistent thermal stress. So think about differential expansion. The glass might handle the radiant heat very differently than the aluminum or the steel mullion frame. Right.
If that heat builds up in those upper aluminum sections, you get overheating in those specific mullions. And this just subjects the material tolerances to constant, rapid thermal cycling.
And the consequence of that cycling isn't just, uncomfortable heat inside. It's a critical failure mode.
Oh, absolutely.
You risk premature degradation of the sealant, you compromise the weather tightness, and worst of all, you're looking at metal fatigue.
So when we look at the life cycle cost of these specialized skins, the detailing of that fixed clip and the spandrel pocket, it becomes exponentially more important than the glazing panel itself. It's a high-stakes calculation.
So you're balancing photon capture against connection integrity.
Precisely.
Okay. So moving from capturing light to stabilizing the ground, we're shifting focus to a critical new subdiscipline. This is emerging in deep cold infrastructure, electrical geotechnics.
And this is vital in permafrost regions, places like Reykjavik, Shenyang, where conventional foundations just struggle against frost heave. Microcurrent arrays buried in the permafrost. That sounds incredibly energy intensive. And the mechanism they're targeting is frost heave, which is that upward swelling of soil when the moisture freezes.
Right. It forms ice lenses, creates this destructive pressure on foundations.
So how can a low-voltage pulse, which is fundamentally a non-thermal process, how does that prevent ice from forming?
That's where the physics gets really fascinating. The goal isn't bulk heating. I mean, that would be incredibly inefficient, and it would destabilize the permafrost by melting it.
Right, of course.
Instead, they're using these low-voltage pulses to interfere with the migration of moisture, specifically the capillary action that draws liquid water toward the freezing front to feed those growing ice
This
lenses.
is an electrochemical thing.
The pulse disrupts the electrochemical bond between the water molecules and the soil particles. It effectively reduces the ability of water to mobilize and form those destructive ice lenses. And that, in turn, reduces the frost heave displacement.
But wait, if you're introducing electrical conductivity into, heterogeneous soil, doesn't that inherently risk uneven resistance?
It does.
Couldn't you accidentally create thermal pockets, especially if the soil matrix changes? I mean, that localized melting would be far worse than the original heave.
That is the core geotech challenge. The complexity lies entirely in the power distribution system. You have to design the trenching and the array placement to maintain what we call electrical isotropy, an even spread of the microcurrent, while simultaneously ensuring the system does not generate any thermal hotspots.
So how do you mitigate that risk?
The systems rely on continuous low amperage pulsing and integrated ground temperature mapping. The structural stability of the entire foundation now depends on the seamless integration of advanced electrical controls and sub-zero soil physics. You are actively managing the phase change of water molecules using infrastructure.
Incredible. Okay, let's shift focus. Let's look at how automation is changing construction sequencing and how biology is changing the building envelope. We'll start with an operational advantage being exploited in major urban centers like Singapore, Toronto, Vienna.
Night shift concrete finishing.
Exactly.
This is a textbook example of using AI and robotics to move high-precision activities out of that variable, human and environmental window. They are deploying AI-guided finishing robots that operate exclusively after sunset.
And the main advantage is reducing solar curing variability. Why is that so detrimental to a high-precision slab, say, in a data center or industrial floor?
Because concrete curing is an exothermic reaction. It generates its own heat.
Right.
If that slab is exposed to direct daytime sun, the surface heats up dramatically faster than the core or the base. And that leads to differential shrinkage, thermal stress, and microcracking.
And that gives you slab curling.
Yeah.
The floor surface is uneven.
Exactly. And then you need extensive, costly remediation later, or even worse, it fails to meet the flatness tolerance required for automated storage systems.
So operating at night when temperatures are stable and there's no solar radiation, that allows for a much more controlled, homogeneous curing process. Better flatness, better longevity.
Right. And that structural advantage forces a really radical shift in construction sequencing. Construction is no longer 9 to 5. It's a 24-hour adaptive cycle.
Which means the work the robot does at night has to be accepted and integrated by the human teams during the day. That sounds like a major quality control challenge.
It is. We need a nighttime QC protocol that can seamlessly merge the autonomous robotic slab data, which might include extremely granular real-time laser leveling metrics, material temperature profiles, with a human-verified tolerance check.
So the human role shifts from being the finisher to being the auditor.
That's a great way to put it. It requires new protocols for lighting, for calibration, for documentation transfer, all to make sure the liability of the finished product is clearly assigned without slowing down that 24-hour flow. It's auditing autonomously achieved precision. That's a new skill set entirely.
From automation, let's go even further afield, into bio-innovation. This is really the idea of the building envelope as a living system.
Biothermal cladding. This is being tested in environments like Anchorage, Tromsø, and Yakutsk.
And this is where architecture really becomes microbial engineering.
It is. The building envelopes are infused with these microbiofilms, engineered layers of biological material, maybe specific algae or bacteria that act as living thermal shields.
And their function is to activate gentle, controlled exothermic reactions. So as a byproduct of their metabolism, they release heat.
And that heat warms the surface layers of the cladding during the deepest, coldest winter cycles.
So we have a system that uses biology to actively regulate surface temperature. It provides passive heating that could, for instance, prevent surface ice buildup or reduce the thermal gradient shock across the assembly. But biology is dynamic. Any active metabolic process, it requires maintenance. It produces movement, however small.
And that brings us directly to the cladding challenge. Any exothermic activity, a biological system gently warming and cooling, causes cyclic microexpansion and contraction of the panel material.
So the structural fix is all in the detail of the fix clip.
Yes. We must design the mechanical connection to accommodate that micro-expansion without failing the facade over decades of this subtle movement.
If that fixed clip, the fastener holding the panel, is too rigid, the constant subtle stresses will induce material fatigue, creep, and ultimately clip failure.
Which risks the integrity of the entire weather envelope.
And if the expansion isn't properly accommodated, you might get tiny microgaps that introduce moisture and risk long-term condensation corrosion, ironically caused by the system designed to stabilize the thermal environment.
So the success of this, futuristic living facade relies entirely on the quality of a few millimeters of mechanical tolerance at the connection point.
Let's pivot now from climate adaptation to large-scale structural resilience, specifically in high-risk seismic zones.
We're focusing on seismic phase timber towers. These are being developed in Japan, Chile, and Turkey. The goal here is to evolve laminated timber from just a low-carbon structural material into a controlled deformation seismic device.
So this is way beyond simple mass timber construction. The core mechanism involves using laminated wood assemblies, CLT or glulam, with embedded sinusoidal cuts.
Physically introducing a wave pattern into the panel geometry.
Why a wave pattern?
It functions as a predefined point of controlled weakness, a structural fuse, if you will.
Yeah.
When the building experiences a seismic wave, instead of the structure acting rigidly and transferring maximum force to the joints, these cuts allow the panels to deform and flex in a calculated, non-linear way.
So the sinusoidal geometry disperses the seismic wave energy across the building perimeter before it can concentrate and cause a brittle failure.
Exactly. The timber itself becomes an intrinsic damping element.
That is a fundamentally elegant approach, using the material's geometry to dissipate energy, which is usually done with these bulky external steel dampers. But if the perimeter panels are designed to intentionally flex and move, the most critical vulnerability has to be the connection challenge, especially at the corners. How do you allow these wave-damp panels to dissipate energy by deforming without absolutely rupturing the facade continuity?
It's a spatial and material paradox. The structure might need to move by several centimeters in a major event, yet the facade has to remain fully operational. Weather-tight, fire-resistant.
That requires a highly complex multi-axial joint that can absorb translation, rotation, and compression all at the same time.
And the corner detailing has to be redundant enough to allow for that seismic movement while returning to its original state afterward, all while maintaining the integrity of the cladding and glazing interface.
So you're adapting bridge technology for buildings.
In a way, yes. This is where advanced elastomeric seals and sliding panel systems, usually reserved for long-span bridges, are being adapted for vertical architecture.
Okay, finally, in this section, we're looking at the convergence of architecture, policy, and social necessity with something called modular water rights architecture.
This is not just a building. It's a piece of civic infrastructure designed for mobility. It specifically serves regions facing extreme resource stress places like Zambia, India, the American West.
The purpose is to provide immediate, flexible, and impartial venues.
Yes, these are civic pavilions designed to travel between decentralized communities along river systems to host critical functions. Water rights, arbitration, environmental mediation, regional planning forums. It's about making the administration of resources responsive and accessible.
Which introduces a fascinating planning challenge for the design teams. The modular layout has to accommodate two vastly different modes of engagement that often happen simultaneously within the same dispute.
Exactly. On one hand, you need to support the formality of adjudication, the structured, legal, highly linear process of settling disputes. That demands clear hierarchy, security, acoustic separation for confidential proceedings.
And on the other hand,
it must enable the flexibility required for informal community negotiation. The softer, dialogue-driven process where trust is built, where maps are spread out, and consensus is sought among varied stakeholders, often over long adaptive sessions.
you can't solve a water dispute with a single rigid courtroom.
No, the modular system has to be instantly reconfigurable. From a highly formal tribunal, setting clear sightlines, defined authority to an open, non-hierarchical town hall setting, maybe even semi-open air, that facilitates compromise. The structure's ability to foster trust is as important as its ability to withstand transport and deployment.
Okay, let's shift now from component-level innovation to a macro strategic opportunity that really synthesizes everything we've just talked about.
The integration of engineering, governance, and architecture on a massive scale.
We're looking at a major international initiative, the Intercontinental Port Resilience and Maritime Governance Center. It's earmarked for a strategic location in the Western Pacific Rim.
And this is not a typical construction project. This is the physical embodiment of global maritime policy.
The scope is immense. It demands a multidisciplinary approach right from day one. Look at the range of specialized spaces required.
You have dedicated structural wave tank labs for coastal defense modeling. You have custom simulation courts for legal training, high-tech port security scenario theaters for crisis management,
And integrated coastal ecology observatories. It's a campus built at the intersection of science, security, and law.
It is.
And this project fits perfectly into the advanced intellectual framework we championed, combining high-level structural engineering aptitude, deep governance insight, regional planning skills, and coastal urban strategy. This is the definitive opportunity to develop maritime urbanism as a signature intellectual framework.
And maritime urbanism in this context, it moves beyond just drawing a line around a port facility. It's the formal recognition that the physical infrastructure, the piers, the breakwaters, the navigational aids is inseparable from the civic and political life of the region.
It's where global trade, national security, climate resilience, and local communities all meet.
And often clash, yes.
The strategic angle here seems pretty clear, positioning the center as a maritime diplomacy engine.
Right. The architecture itself has to physically represent that complex balance of power. It's a campus where physical infrastructure and supranational governance, the agreements between nations, are architecturally intertwined.
So the building isn't just shelter, it's a tool for diplomacy, communicating stability or fluidity through its very design.
And that brings us to the most profound design challenge of the RFP, the central architectural challenge. We have to define a central hall that physically expresses the negotiation among three powerful, often conflicting forces.
Which are?
The dynamic, massive, and unpredictable ocean forces, the highly controlled, efficient, and rigid demands of trade logistics, and the need for transparent, permanent, and fair public authority.
That is structural semiotics at its absolute highest level. How do you make trade logistics feel efficient and swift while making public authority feel permanent and just, all within a space that reminds everyone present that they are fundamentally at the mercy of the ocean's power?
The tension has to be built into the walls.
Wow.
And the specific design prompt, the Coastal Diplomacy Rotunda, is particularly insightful. It calls for a circular chamber using geometry and structure with the critical constraint of no literal maps or maritime symbols.
So you can't just hang an anchor on the wall.
No anchors, no waves painted on the wall. The architecture itself must express shifting maritime power and support both highly formal, ceremonial negotiation and high-pressure, closed-door bargaining.
So we're asking the structure to do the communicating. You might use, what, massive, grounded lower columns representing the permanence of public authority.
And you could juxtapose that against a ceiling plane defined by highly complex shifting geometries, maybe lightweight tensile structures, that represent the fluid, unpredictable nature of the ocean or global commerce.
And the way light enters the space,
Yeah.
maybe controlled by tidal simulations or reflecting the changing weather, that becomes the diplomatic variable.
Exactly. The entire structural and material vocabulary must convey the complex, constantly changing power dynamics inherent in maritime governance.
Okay. Let's shift gears now for the structural deep dive. This is the ARE study block.
Right.
This is where we focus intensely on critical, often overlooked structural physics that define specialized architecture. These are the secondary, dynamic, or thermally induced loads that frequently lead to localized failure if they're not explicitly modeled.
Yeah, these are the forces that, they sneak up on the conventional load calculations because they stem from thermal effects or dynamic occupancy or internal industrial processes rather than just standard wind or seismic codes.
We'll start underground with facilities using geothermal wells.
Yeah.
We have to analyze well cap thermal bowing. Why is that a major concern?
Well, geothermal systems use the Earth's heat, but that thermal energy isn't perfectly contained. Thermal gradients naturally cause heat to migrate upward toward the surface. When that heat hits the large, rigid concrete cap covering the well, it causes differential expansion. The center of the cap gets warmer and expands faster than the perimeter, which is tied to the cold ground.
And that leads to the cap bowing or uplifting slightly. What's the structural consequence of that minor movement?
The movement fundamentally alters the load transfer patterns across the foundation. The cap uplift creates a thermal push, an unanticipated vertical force, which introduces localized shear and bending moments into the foundation system. Critically, this creates foundation differential behavior.
So one section is pushing up, while the one next to it is just reacting to dead load.
Yes, and you introduce stresses that were never accounted for in the original structural analysis. You risk localized cracking or even failure in nearby grade beams or slab sections. This is a perpetual motion thermal stressor.
Okay. Next up, the seemingly benign environment of a library. Why do we need to perform stack compression microdrift analysis? I mean, most designers just model the square footage weight, assuming a static load.
Libraries are deceptively challenging structures because they contain extremely high concentrated point loads, the bookshelves. When you have high-density shelving, you are creating massive, localized inertias.
So when a lateral event occurs, a minor seismic tremor or even major wind buffeting, those concentrated point loads act as massive inertia points, and they try to move independently.
Right. The result is slab deflection, but more importantly, a lateral stiffness imbalance. The slab is loaded heavily in dense areas and lightly in reading areas. This uneven distribution of massive inertia means the books themselves amplify the dynamic movement, causing microdrift in those high-density zones.
So the slab isn't responding as one monolithic piece.
Not at all. We need to design the floor plate not just for vertical capacity, but for an exceptional level of stiffness to resist that concentration of lateral force. If you ignore it, the uneven response can skew the entire structural system's dynamic response, potentially shifting unintended seismic forces into nearby shear walls or columns. It transforms the library from a simple storage facility into a complex dynamic system.
Moving to high-performance industrial, waste-energy plants, we have to evaluate chimney draft shear reversal. That sounds counterintuitive.
It's pure dynamic fluid physics applied to structural engineering. In these plants, the rapid movement and acceleration of flue gases up the tall chimney stacks create a dynamic pressure differential. High-velocity gases can create suction or negative pressure near the walls, particularly at changes in geometry.
So the internal flow dynamics introduce an external load.
Yes, and that load is often in the opposite direction of the prevailing wind load. That's the opposite direction shear.
So if you're modeling your sport frame to resist a 100-mile-per-hour wind from the west,
but the internal draft dynamics simultaneously pull the frame eastward, you are subjecting the connections to a high-frequency load reversal. This can dramatically impact diaphragm anchorage and cause rapid material fatigue and failure in support elements that weren't designed for oscillating bidirectional stresses.
wow. Okay, our fourth area. Complex multi-level transit nodes. Two critical issues here. First, piston wind concourse dampening.
This is a major serviceability and safety concern. High-speed trains, particularly when braking in enclosed tunnels or stations, displace a massive volume of air, the piston wind, creating rapid, large-scale air pressure surges.
And if that pressure surge hits a concourse or a ticket hole,
it causes intense glazing vibration and severe occupant discomfort.
we're talking about air pressure acting as a literal sudden load, causing window glass to rapidly deform.
Precisely. The challenge is engineering concourse dampening systems, ventilation shafts, pressure relief zones, acoustic baffles that can absorb this energy surge rapidly and safely. If it's not addressed, fatigue failure of the glazing system is a real possibility, and the sudden pressure change can be extremely disorienting, even dangerous for occupants.
And the second issue in transit nodes is picket hall compression pools. This happens at bottlenecks like fare gates or escalators where people cluster.
The load imposed by hundreds of people is not static. Human load dynamics are complex. When heavy clusters form, the micro-movements, shuffling, stopping, starting induce local slab compression waves. It's a rhythmic, localized pulse of stress propagating through the floor plate.
So it's not the sheer weight, but the localized dynamic response to that high density.
Exactly. If the slab is too flexible or lacks sufficient local stiffening, this dynamic clustering can cause localized cracking and serviceability issues. This is why you need flow-based structural design, moving beyond the simple PSF calculation and into human dynamics modeling to ensure the floor plate can handle these transient compression pools.
Next, in academic and research environments, we have a classic serviceability problem. Corridor resonant walking frequencies in mid-rise buildings.
This often plagues structures with long, slender corridors or open-plan offices where the floor system is tuned to certain frequencies. If a large group of occupants, say, an entire class walking together, unintentionally synchronizes their rhythmic loading, they can hit the natural frequency of the floor plate,
which dramatically increases the slab vibration amplitude.
Right.
What might feel like a minor annoyance in an office becomes a serious structural concern in a sensitive research lab.
It can render sensitive instrumentation useless, cause nausea, or simply make the building feel seismically unstable every time a class changes. This necessitates extremely careful deflection control and often requires the use of tuned mass dampers or stiffening girders specifically placed to detune the corridor plate from common walking frequencies.
Related to research hubs, especially data centers within academic facilities, we have server rack lateral sway stacking. What's being mitigated here?
Server racks, though non-structural, represent massive, concentrated, and often poorly anchored mass. In research hubs, these can be stacked floor upon floor. During minor quakes or even high wind events, the inertia of these racks, especially if they are tall and slender, causes multi-floor sway.
So that non-structural mass dramatically amplifies the movement in the upper stories.
Yes. This mass amplification significantly alters the interstory drift calculations. The lateral bracing elements, the shear walls, the frames that were designed for the structural mass suddenly have to handle the dynamic inertia of tons of unanchored equipment. This makes anchoring protocols a critical life safety and business continuity issue.
And specialized industrial facilities, two more. First, reactive tank lateral surge tests in water treatment labs.
This is critical in facilities dealing with large liquid volumes that are subject to agitation or rapid mixing. If the tank is only partially full, which is common during processing, chemical agitation causes the liquid to create dynamic lateral waves. It's known as slosh coupling.
So instead of a nice predictable hydrostatic load, you have dynamic waves slamming into the walls.
Exactly. These forces are unpredictable, asymmetrical, and can far exceed static liquid pressure loads. They have to be rigorously modeled because they create dynamic pressure pulses that slam into the tank walls, severely impacting beam shear and the overall tank anchorage integrity. Failure here means environmental disaster.
And still in cold regions, we're looking at frost curtain anchor verification in cold region warehouses.
These industrial cold storage facilities use fabric frost curtains or specialized air channeling systems to maintain massive temperature differentials between loading docks and storage zones. The channeling of intensely cold air creates concentrated stress on the anchorage points where the curtain meets the structural frame.
So the very system designed to manage the cold environment inadvertently introduces a structural fatigue risk.
Yes. This cyclical stress on the anchors, combined with the extreme temperature gradient, leads to connection fatigue. And crucially, it causes condensation when the warm air meets the cold steel, driving accelerated, condensation-driven corrosion. We have to verify these anchors aren't just strong enough to hold the curtain, but resilient enough to withstand decades of thermal and moisture-induced fatigue cycles.
And finally, let's wrap this section with envelope and tilt-up structures. We need to assess panel toe thermal shear drift.
Tilt-up concrete panels are massive structural elements that define the envelope of many warehouses. The issue arises from uneven solar heating. The lower panel zones, the panel toes, are often shaded or partially buried, while the upper sections bake in the sun. This temperature stratification alters the shear transfer at the base connection.
The differential expansion causes the panel to try and move slightly across the floor slab.
Precisely. This uneven heating introduces thermal shear stress at the panel toes. This shear imbalance causes rapid cyclical anchorage fatigue at the base connections. And if those connections, the primary lateral load path for these massive walls, fail, the entire structure's seismic and wind resistance is compromised. It is a textbook case of thermal environment becoming a structural liability.
That rapid-fire session really highlights how often we miss these dynamic secondary forces in design. Now, let's solidify that lesson with two specific operational scenarios that confirm our central thesis: that environmental forces inevitably become structural forces.
Okay, scenario 1. A highly controlled biotech facility where the very air we breathe is acting as a measurable load path. The problem is humid air uplift pockets forming above ISO 7 sterile corridors.
ISO 7 sterile corridors require positive pressure. You're actively pushing air in faster than it can escape to prevent particulate infiltration. And this HVAC overpressurization, measured here between plus 0.05 and plus 0.09 inches of water gauge, is causing the ceiling grid to physically lift.
The data showed a measured uplift of 2 to 4 millimeters across a 2.6 meter wide ceiling span. While that seems minute, the risk is existential for the operation.
Because that movement causes gasket failure.
Gasket failure, which is followed by particulate infiltration and, worst of all, a microbial breach of the sterile zone. The air pressure is behaving exactly like a distributed uplift load on the ceiling grid and its connections.
So the lesson here isn't just technical, it's almost philosophical. Airflow is a structural force. Pressurization geometry must be engineered like load paths. You can't just treat HVAC as a separate system.
Right. And the mitigation required intensive work. Mapping the air leak paths, introducing pressure balancing transfer ducts to relieve excess pressure, and structurally upgrading the ceiling suspension system. They had to introduce secondary hold-down clips and reinforce the gasket ceiling to physically resist that 4 mm uplift force that the HVAC system was generating.
You are structurally restraining the positive pressure.
Exactly.
Okay, scenario 2. This deals with a mountain campus facility where an intentional modification to the ventilation system unintentionally altered the roof's structural behavior.
The problem: cold air sink sagging in long-span roof trusses.
The structure featured 32-meter span trusses. After new ridge vents were installed to improve thermal circulation, the team measured an unanticipated 5 to 8 millimeters of mid-span sag.
The investigation revealed that the new vents were inadvertently drawing in and pooling an extremely dense layer of a cold air sink, about 0.9 to 1.4 meters deep on the interior of the roof structure.
The cold air, being denser, accumulated and acted as an unexpected, massive, localized dead load right across the midspan of the trusses.
It was essentially like putting an unmodeled water tank in the middle of the roof structure.
And this proved that ventilation geometry can unintentionally alter roof load behavior. Air patterns have to be treated as structural influences.
The fix wasn't just mechanical. They had to install air mixing baffles to prevent the dense pooling. And structurally, they had to reinforce the truss mid-panels with tension rods to compensate for the permanent, unanticipated downward stiffness requirement induced by those air patterns.
Okay, let's move to specific code mastery, beginning with Code Byte 1, IBC 1616 diaphragm flexibility. We need to focus on the complexity of designing mixed material buildings.
Structures combining, say, steel frames, cross-laminated timber floors, and concrete shear walls.
Right.
When you combine these materials, the critical insight is that a composite diaphragm, even if it's technically connected, is not automatically rigid under seismic load. The stiffness ratio between CLT, which is flexible, and concrete, which is rigid, is vast. Transitional stiffness breaks occur at the junctions between these differing material zones.
And if the stiffness suddenly changes, the seismic load path changes unexpectedly.
Exactly. These transitional breaks redefine where the lateral forces are collected and transferred to the vertical elements. If the diaphragm shifts from a stiff concrete zone to a much more flexible CLT zone, the collector elements, the beams designed to gather that lateral force, must precisely match the stiffness of the material they are serving.
Assuming it's all one monolithic, perfectly rigid system will lead to catastrophic overloading.
Overloading of the connection points and potential failure in the more flexible element. This demands highly sophisticated mixed logic seismic thinking.
Our final operational check, Code Byte 2, NFPA 101, exit discharge slip gradient zones. This is a practical, ground-level life safety lesson that's often overlooked in material selection.
Egress paths, the immediate routes leading away from a building, they must account for gradient-induced slip risk. This is especially critical when slopes exceed 1.2. When that slope is combined with moisture, the risk of a mass casualty event due to slipping and falling during an emergency rapidly increases. Safety relies on materials maintaining traction under wet conditions, a standard often neglected during material specification.
So egress isn't just about direction and capacity, it's about friction.
It is entirely frictional. The ultimate takeaway is that egress is not just directional, it is frictional, relying on the synergy between the slope, the surface material, and the lighting provided.
Lighting too.
Yes, NFPA 101 even suggests increasing lighting levels in gradient and moisture-prone zones because human perception of slip risk decreases significantly in low-light conditions. Failure to integrate all three of those elements compromises the rapid, safe movement of occupants during a high-stress emergency.
Okay, we're finishing our technical mastery session by presenting a pure conceptual challenge, a thought experiment that tests the limits of structural form. The Seismic Weave Pavilion.
This is an exercise in structural elegance that aims to solve a performance problem through pure geometry rather than mechanical technology.
The constraints are stringent. The pavilion must use the geometry of weaving beams to dissipate lateral loads. Columns have to remain strictly orthogonal, straight up and down, and crucially, no dampers are allowed.
This challenge forces a total integration of the lateral system into the architectural expression. Think of a basket weave or a complex reciprocal frame logic. The structure itself, through its intersections and its curvature, must provide the necessary stiffness, redundancy, and energy absorption capability.
So the weaving geometry has to be mathematically proven to act as a passive energy dissipation system, while also defining the space below.
Exactly. It tests whether we can achieve resilience purely through structural form and material choice, eliminating reliance on added-on technologies like viscous dampers or specialized isolators. It asks, can the architect be the engineer by defining the load path through the poetry of the curve?
Let's take a moment for reflection now, connecting the hyper-technical details of the morning back to the macro challenges of global practice.
Our first reflection point is fundamental to this entire dive. Where does climate behavior err, cold, heat, or sound shift from environment to structure?
We saw repeatedly the cold air sink, the humid air uplift, the thermal bowing of the geothermal cap. Air, temperature, and moisture are not just environmental conditions handled by the MEP system.
No, they're quantifiable loads.
Exactly. The moment a climate condition causes a measurable deflection, a material fatigue cycle, or a change in shear transfer, it has become a structural force that has to be modeled by the engineer.
And our second reflection point brings us back to that high-stakes world of the international RFP. Where do environmental forces become diplomatic forces in architecture?
This is the crux of the Maritime Governance Center. The ocean forces, rising sea levels, coastal erosion, unpredictable storms. They aren't just design constraints. They're the external threat that drives the very need for supranational negotiation.
Therefore, the architecture that houses those negotiations must spatially acknowledge that monumental power. By structurally expressing the fluid and unpredictable nature of the ocean, perhaps through dynamic geometries or materials, the building positions the environment as the ultimate third party in all diplomatic agreements concerning the sea.
So the structure itself becomes a constant, non-negotiable reminder of the urgency of resilience and cooperation.
Exactly.
We have covered immense ground today, moving seamlessly from a sub-millimeter scale of microexpansion in biocladding and the thermal shear drift at a tilt-up panel's toe, all the way up to the multi-continental scale of maritime diplomacy and governance frameworks.
And the key lesson for the advanced practitioner remains consistent. AEC mastery requires not just deep technical skill in one discipline, but a radical capacity for interdisciplinary thinking. You have to train yourself to see climate, politics, material biology, and airflow as active structural challenges.
Every technical detail we discussed today, from preventing condensation corrosion on a cold region anchor to understanding the dynamic response of a slab to a pedestrian compression pool, it builds the foundation you need to tackle major international RFPs and define the future of integrated, resilient urbanism. Your transformation into a global, multidisciplinary design authority continues.
To conclude, we'll leave you with one final provocative thought for your reflection, something to explore in your own practice. How do you architecturally express complex, invisible forces, whether the microexpansion of biocladding, the dynamic push of piston wind, or the supranational negotiations of maritime law? Think about how the unseen defines the structure and what that structure communicates to the people inside it. Until tomorrow.